guys, welcome to today's video on parallax and the cosmological principle. This is going to be really important if you're doing OCR A. So we're just going to jump straight in with what parallax is. So we're going to imagine that we want to measure the distance to a star. So I've got my star over here. Now, this down here is going to be the sun, and orbiting around the sun, we know that we have got the Earth. So what we're going to do is we're going to pretend that we are an astronomer on Earth and we point our telescope at this star. And we're going to measure the angle that we point our telescope at. Now we're going to wait 6 months because 6 months later, the Earth is going to be on the other side of the sun over here because we'll have gone around the sun. And now we're going to have to point our telescope at a slightly different angle to get to this star. This angle in here can be measured. Now, if I draw a line down the middle, this is going to look like something that we know a little bit better. So if I make this into a right angled triangle, suddenly we can use trigonometry to work out the distance to this star. Now, trick here is we're going to use the small angle approximation. In fact, parallax angles are often so small that we've invented a new unit of angles for them called the arc second. The arc second is 1/3600th of a degree. So an arc second is a really, really, really tiny fraction of a degree. And parallax angles are so small that we normally measure them in arc seconds. So this angle here between what's going to be the vertical and this line here, that is our parallax angle. Parallax angle, which is abbreviated to P. Now, this distance here is the distance between the sun and the Earth. Now, this is actually often known as 1 astronomical unit, which is linked over here for you. 1 AU, which is 1.5 times 10 to the 11 meters. That is the average distance between the sun and the Earth. So if we know the angle and we know the length of one of the sides, we can work out one of the lengths of the other sides. Now, it doesn't actually matter which of these sides we work out, whether it's the sun to the star or the Earth to the star, because at really small angles, they're going to be roughly the same size. Remember, we're measuring the distance to a nearby star. It's not like it's next door, so realistically, it doesn't actually matter if we're measuring which side we're going to measure. So we're going to use tan theta is equal to the opposite over the adjacent. Now, at really small angles, we can use the small angle approximation, which tells me that tan theta is approximately equal to just theta. So here I'm just going to have that the parallax angle is equal to the opposite, so that'd be 1 AU divided by the distance between the sun and the star. And that's what we're looking for. We're looking for that distance that the star is from us. Okay. Now, I'm going to rearrange this. So I've got distance is equal to 1 AU divided by the parallax angle. And now we're going to introduce you to a new unit for distance called the parsec. Okay. So it's a measurement of distance. And a parsec is defined as the distance when the parallax angle is 1 arc second. So if your distance is in parsecs and your parallax angle is in arc seconds, we get this lovely formula here, that distance is equal to 1 divided by the parallax angle. So for example, let's say we wanted to work out how far away a star was that had a parallax angle of 0.2 arc seconds. We just do distance is equal to 1 divided by 0.2, and that would give me an answer of 5 parsecs. If we then wanted to find this in meters, we could use our 1 parsec conversion, because 1 parsec is 3.1 times 10 to the 16 meters. And there we go. So this is where the equation comes from. The key thing to remember when using this equation, though, is distance has got to be in parsecs, and your parallax angle has got to be in arc seconds. Right. The other thing we just want to go through in this video is the cosmological principle. So the cosmological principle states that the universe is homogeneous and that it is isotropic. Isotropic means it's the same in every direction. So no matter where I look in the universe, it should be the same in every direction. And homogeneous means that matter is roughly uniformly distributed. So if we take a large chunk of the universe, it should have the same density as any other large chunk of the universe. And there you go. That's parallax and cosmological principle all done for you.